All right, we're going to talk about the electric field. And to do that, we are going to start with the example that we were looking at for the Coulomb force law, the force due to multiple source charges. So, to remind you, we have 8 source charges here. Let me just highlight all of them. So I've got 8 source charges. And in that problem, we were trying to figure out, all right, what is the force on this test charge, this plus Q? And what we ended up getting for that force, that net force due to all of these contributions, was this expression that I just highlighted, where we were able to essentially write out the expression as the sum of all of the contributions from the source charges and then multiply that by the test charge Q. And what we're going to do is we are going to isolate this term that I just highlighted, and we're going to call that the electric field. And so I can rewrite the expression for the force on this test charge as Q times E, the electric field, where the electric field is defined as this expression. It's the summation part that was in the previous expression. And the E field is due to the source charges. Right, so when I say E field, I'm referring to the electric field. Now, a few details about the electric field. The electric field is determined by the source charges. The electric field is a vector, which means we've got magnitude and direction. For discrete source charges, the magnitude of the electric field generated by a point charge is given by this expression. And the direction of the electric field is along the straight line R. So if you look up here at this picture, if we want to find the electric field at this spot right here, we've got our charge Q, and then we've got this line, this straight line, this distance R, between the point where we're interested in finding the electric field and the source charge itself. The electric field points away from the charge if it's positive, or towards the charge if it's negative, right? So that's the convention. The unit for the electric field is newtons per coulomb. And let's take a moment to think and talk about what is the electric field. The electric field is a way to represent how space is distorted due to a source charge. Another way to think of it is the electric field allows us to predict what force a charge Q will experience if it's placed at that location. All right, so let's talk about this a little further. So we are going to talk about the electric field as an analog to the gravitational field, or an analog to what we've discussed with gravity. If you remember, the expression for the universal law of gravitation is what I've just circled, where you've got the gravitational constant multiplying both m1 and m2, so gravity is the force between two masses, and then divided by the separation between those masses squared. Now, of course, in 101, for the most part, we were near the surface of the Earth, and so m1 was really the mass of the Earth, r12 is really the radius of the Earth, and if you plug in those numbers into the force of gravity expression, what you end up getting is that the force of gravity on an object near the surface of the Earth is going to be equal to 9.8 newtons per kilogram times m2, and then the direction there is towards the Earth, towards the center of the Earth. And of course, this should be very familiar whenever we calculated the force of gravity on an object near the surface of the Earth. We used the expression m little g, where little g was 9.8 meter per second squared. And you'll notice that Newton per kilogram, right, just so happens to be equivalent units as meter per second squared. But the idea here is that Newton per kilogram, this represents the gravitational field of the Earth. So for a mass placed in the gravitational field of the Earth, the mass will experience 9.8 newtons of force per kilogram of mass. With the electric field, we have the exact same scenario. For a charge that we place in an electric field, the charge will experience however much the magnitude of the electric field worth of Newton's force per coulomb of charge that charge possesses. All right, so we've just introduced the electric field, and so what I'm going to do now is work through this example from the textbook. Again, pause right now and try to work through this on your own, and when you get done, unpause and follow along. Okay, so for this particular problem, we are given two source charges. So I've got my two source charges, and we are trying to find the electric field at some location P up here. And so I've already sketched out the electric field vectors, and so let me just go through those real quick. So the electric field vector due to charge Q1 at this spot is going to look something like this. We know that the vector is going to point away from the positive charge because that's how we've defined the direction for the electric field. And for Q2 over here, the electric field at this spot is going to look something like that. And so if we want to know the electric field at that location P, we're going to have to add those two vectors together. And what I've already done is broken up the vectors E1 and E2 into components. And you can see we've got x components of E1 and E2, and it turns out, since the vectors E1 and E2 have the same magnitude and they're at the same orientation, that these two components in the x direction are going to cancel out. And then we've got the two components in the vertical direction, and those are going to add together. And so if we can figure out the magnitude of E1 and E2, and then using this angle right here, find the component of that vector that's pointing upwards, then we can immediately find the electric field at that location. All right, so first notice that this problem is symmetric, that Q1 is a distance d over 2 from this vertical axis, and then there's a distance z, and then it's identical on the other side, d over 2, and then the height z. And so what this means is that really all we have to do is find the magnitude of one of these vectors, and then we just have to multiply by 2 because there's going to be two contributions, one from each of these charges. So how do we find the magnitude of the electric field of a point charge? Well, we just use this expression right here. And so E1, so the magnitude of E1 is going to be 1 over 4 pi epsilon naught Q, and then R squared. But what is R squared equal to? If we look at my picture here, so this is R. So what is R squared equal to? Well, R squared is going to be equal to this term squared plus this term squared, right? The Pythagorean theorem. So we've got d over 2 squared plus z squared. And so I can put that in for E1. All right, so that's the magnitude of the vector E1. But remember, what I want is to then find the component that's vertical, right? How much of this is pointing straight up? And so if I sketch this over here, so I have this vector E1. And if we look at the picture, we can see that the angle theta here, right, that angle is measured from the vertical axis. And so this angle, if I zoom in, this angle right here is also theta. So that means we want the cosine of that vector to get the vertical component. So this is theta right here. And so E1y, 1 over 4 pi epsilon naught q over d over 2 squared plus z squared, and then cosine of theta. Now, the other thing we can do is recognize that if we look at this big triangle, if we look at that triangle, well, according to this, cosine of theta is equal to z over r, which is the same thing as z over d over 2 squared plus z squared to the 1/2. Right, because this is equal to r. So I can swap out the cosine theta term. And this simplifies. To that expression. And so here is one of the vertical components. And so if we want to get both contributions, then we basically just need to multiply by 2. So E at that location is going to be and if we want to include the direction, if you look at this picture, I didn't actually designate my axes, but I did right here. So I'm going to call that the plus j hat direction. And that's the end. All right, the last thing that we want to touch on is the idea of an electric field produced not just by individual point charges, but also continuous charge distributions. So just a refresher, for a discrete set of charges, and that's what I've got pictured over here, 3 point charges. If I want to find the electric field at this point, P, I use the expression that I introduced on the previous page. Now, if I have a continuous charge distribution, right, so my source charges are distributed in a continuous manner, and we have 3 ways that this can happen: along a line, along a surface, or throughout some volume. If I have those distributions, the expression to calculate the electric field at a point P changes slightly. And so the first thing that happens, and let's focus on the line first. When I have the line expression here, or the line picture, lambda is the linear charge density, similar to how mu was the linear mass density. So that's the linear charge density. And when we're going to determine the electric field, basically we need to divide up the line into small chunks, dl, and integrate, basically. So over here, I have the expression for how to calculate the electric field due to a line of charge. And I'm just going to circle. In the discrete case, I have a summation. And in the continuous case, I have an integral. In the discrete case, I'm summing over the charge elements Q. And in the line charge case, I'm summing over the charge element lambda dl. Right, so the units for lambda are charge per meter. So if I do lambda dl, that's in units of charge, just like in the previous expression. Now, if we move on to the next example, the area, now if I want to calculate the electric field due to this area of charge, in this case this sheet of charge, I have to combine sigma, the surface charge density, with the surface element dA. And so when I do that, my expression turns into this, where I have, again, an integral, and now instead of lambda dl for the line, I have sigma dA for the charge element. And sigma is charge per meter squared. It's the charge per unit surface area. And then lastly, we have the volume example, where we have a volume charge density and our small unit of volume, dV, that's what we have to integrate over. So looking at the expression for calculating the electric field due to a volume distribution of charge, again, we've got an integral, and again, we've got this charge element, now rho dV. So multiplying the volume charge density by the infinitesimal volume element. So rho is charge per cubic meter. All right. The book goes through a couple examples of how to leverage these three expressions for different situations. I'm not going to work out all of that algebra, but I am going to highlight two sort of important cases for the electric field for two interesting distributions of charge. The first one is the electric field due to an infinite line of charge, where the line of charge has uniform charge density lambda. The electric field produced by that distribution, so some distance z away from that line of charge, is given by this expression. And the field a distance z away from an infinite plane of charge, or a sheet of charge, is given by this expression. And in class, we'll go through a few examples where we either execute the integrals that I've just highlighted over here on the right, or we leverage these two sort of limiting kind of special case expressions for calculating the electric field.